Alright, so our first topic for today is actually like a few related topics. I think we're probably going to cover this over the course of a couple videos here. We are talking on my pen will work. We'll see, you've got immersions, submersions, and subimmersions. So we're going to let X and Y be manifolds. So element X in X, element Y in Y, and let phi from X to Y be a morphism such that phi of X is Y. We're going to let M be the k-dimension of X and N be the k-dimension of Y as elements. And definition. We're going to let X bar, that was our setup, and here we're going to let X bar and Y bar be also manifolds. And we have essentially the same setup here, except everything has bars over it. So we have X bar over X, Y bar over X and bar over Y be manifolds with elements bar X and bar X, element bar Y and bar Y, morphism bar phi from bar X to bar Y, morphism such that phi bar of X bar is Y bar. Everything looks the same as before. Then our manifolds X, Y, and their points X and Y, and the morphism phi is said to look locally like X bar, Y bar, X bar, Y bar, phi bar, which we know has the same setup. If there exists open neighborhoods U of X, V of Y, U bar of X bar, V bar of Y bar, and isomorphisms, G from U to U bar, and H from V to V bar, such that, well, there's three properties we need. First off, of course, the image of U under phi has to be in V, and likewise, of course, the image of U bar under phi bar has to be in V bar. Secondly, of course, we want G of X to be X bar, and H of Y to be Y bar. So essentially, we can map up the points and their neighborhoods. And thirdly, following diagram commutes U by phi to V, or we can go by G to U bar. Analogously, we go H to V bar. And here we go phi bar. And we mainly use this when x bar and y bar are linear spaces and phi bar is a linear map, so everything at the barboard is linear, and we take our points x and y to be 0, kind of by assumption is the standard usage of this idea. So, with all that kind of set up here, our first topic of the 3 is going to be immersions. And we start off with a theorem, which is just an equivalence. The following are equivalent. First off, Tx of phi is injective. I think we're carrying over our phi and x and y and all that from above. Secondly, there exists open neighborhoods u of x, v of y, and w of 0 in k to the n minus m, and an isomorphism c from v into u times w, such that, well, first off here, phi takes u into v, secondly, if dotless I here, which I'm going to write backwards, dotless I denotes the inclusion, we can of course identify u with u times 0, which is a subset of u times w. We get the commuting diagram where we have map from u to v of phi, then by our c to w is equivalent to our inclusion. Thirdly, our quintuplet of gas, xy, xy, phi, looks locally essentially we can change the variables it like we saw above. Looks like a linear injection, say phi bar from E to F, where E and F are M and N dimensional vector spaces respectively, of course. Fourth, there exists coordinates of our Fi at x and the Gj at y, such that Fi is equal to Gi composed with phi, for I in the range of 1 to m. One sec, I keep seeing this, and I'm going to put a bit more space for the y so I don't get confused here. Y, n, and 0 is our gj composed with phi for j in the range of m plus 1. Okay, this is m, not n for I. And this is m plus 1 through n. And finally, our fifth equivalent condition, there exists open neighborhoods u of x, v of y, and a morphism. One sec, I gotta rewrite this. V of y and a morphism sigma from v to u such that, I need a new page, such that phi of u's in v, phi carries u to v, and sigma is just a left inverse of phi, giving the identity on u. So 2 implies 3 implies 4 implies 5 implies 1 is all pretty straightforward, so we're going to show the proof for 1 implies 2, which was that we have tx of phi being injective, and then we want open neighborhoods of x and y such that we get a isomorphism C from V to U times W, as you do. Oh, this is supposed to be U times W, I just noticed. I was going to say it doesn't make sense. And we can assume without loss of generality by locality that Y is an open subset of k to the n phi of x is 0, and that the image of the tangent space of phi of x, x of phi, is k to the m times 0 inside of k to the m times k to the n minus m, which is of course going to be k to the n. So we can let W be 0 times k to the n minus m inside of k to the n, and we're going to define a map phi prime from x times W to y by phi prime of x and W being equal to phi of x plus W. Then by the inverse function theorem, phi prime is a local isomorphism at x. Hence, by shrinking down x, y, and w, we may assume assume that phi prime is a local isomorphism. Its inverse, which we can call C, satisfies the desired conditions. And definition: a morphism phi satisfying the equivalent conditions of the previous theorem at x is called an immersion at x. A morphism phi, which is an immersion at all x and x in its domain, is just called called an immersion as a whole. Alright, and that brings us to our second topic, which is going to be submersions. And once again, we start with a theorem for equivalence. The following are equivalent. First one is that the tangent at x of phi is surjective, and you can probably see where this is going from here. These are going to be our equivalent conditions for submersionicity, for being a submersion, I guess would be the better way to say it. Yeah. Second condition is open neighborhoods u of x, v of y, w of 0 in k to the m minus n, and an isomorphism C from u to v times w. First off, we have that phi carries u into all of v. Phi of u covers v, not just into v. Secondly, if P denotes the projection from V times W into V, then U to V through phi, or to V times W through C, and then just projecting onto V by P, this is going to commute. Thirdly, x, y, phi looks locally like a linear surjection, phi from E to F, where E and F are M and N dimensional vector spaces, respectively. Number 4, we have coordinates Fi at x and Gj at y, such that Fi is equal to Gi composed with phi for I between 1 and n. And finally, there exists open neighborhoods U of x, v of y, and a morphism sigma from phi to u such that phi carries u into v and of course sigma is in this case now a right inverse of phi, giving the identity on the codomain. And likewise the proof is just, you see everything's kind of symmetric. You have that symmetry between like injectivity and surjectivity. You see it with all these equivalent conditions. The proof is just symmetric in that same manner. And then we can talk about the definition. A morphism phi satisfying the above conditions at x is called a submersion. At x and at all x and x is, we know, is going to be called a submersion. Alright, remarks. First off, it says that I still need to number these. And being a tau is equivalent to being an immersion and submersion. They say here in this book that at the time when this book is written, they say that the immersion is a common term, but submersion is a Borbach innovation. Sometimes using the phrase phi has maximal rank instead. But I'm pretty sure submersion is pretty common now. Like I said, I've taken differential analytic geometry before, and we just learned the phrase submersion, no issue. I think it's a pretty common one now. Although I will keep in the remark here, sometimes the phrase, it's a good way of thinking about it, I think. Phi has maximal rank is used. which of course is going to mean that Tx of phi is injective if the domain is not bigger than the codomain, and that Tx of phi is surjective if the domain is not smaller than the codomain, of course being equivalent if they are the same size, which is necessary for it to be an étal, I guess. Third, we have an embedding. Is a morphism phi such that phi is an immersion the map from x to phi of x is a homeomorphism. And that's it. Our next topic here is a subimmersion, which I'm going to note is not a phrase that I am familiar with. I would think that it would just be an étal, but I'm guessing it's not going to be. Okay, so what is the definition of a subimmersion? Phi is a subimmersion at x if the following equivalence conditions are satisfied. Well, first we can think of it as being phi looks locally like a composition phi bar x bar mapping by s with some s to z bar mapping by some I to y bar, where S is a submersion and I dotless I is an immersion. Or alternatively, we can think of this as phi looks locally like a linear map. Phi bar from E to F. Of course, these being vector spaces with no constraints on the relative sizes of their dimensions. So I guess this is like like an immersion or submersion, except we don't have any constraints on its tangent space having full rank. And of course, the morphism sigma, which is a subimmersion at all x and x, is called a subimmersion. And we have some remarks. The set of points of x in x where a morphism v from x to y is an immersion. Is, I guess, an immersion, alternatively a submersion, alternatively a subimmersion, is open in X. We have the composition of two immersions or submersions is an immersion or submersion, which is not true for subimmersions. And brings us to a theorem. We're going to work in character 0 here, and the following are equivalent. First off, phi is a submersion at x. Secondly, the rank of the tangent space at x prime of phi is constant. For x prime in U, with U some neighborhood of x. Now, subimmersions having constant rank is pretty obvious by linearity, but we should prove the other direction. We're going to let P be the k-dimension of the image of the tangent space at x of our phi. By locality, we can assume, first off, that y equaling v1 times v2 is open in k to the p times k to the n minus p, and that phi, we're going to assume that phi of x is 0, and that the image of the tangent space at x of phi is k to the p times 0. Now we're going to let pi be the map from k to p times k to the n minus p to k to the p, be projection on the first factor, then pi composed with phi is a submersion. Hence, we can assume, first off, x being v1 times some u2 is open in k to the p times k to the m minus p, and that our proposition of pi with phi being a map from v1 times u2 to v1 is projection on the first factor, and then our morphism phi has the form where phi of x1 and x2 is equal to x1 and psi of x1 and x2. Since t x prime of phi has locally constant rank, assume the rank of the tangent space at x prime of phi is constant on v1 times u2, which is rank p. Phi must be independent. Dependent of x2 in a neighborhood of 0. So my writing's getting messy here, as if it's not usually of 0. We know that d2 psi of x1 and x2 would be 0. Otherwise, phi would have rank just didn't write a bunch of words there. Would have rank greater than p. It's supposed to be just greater than, not greater than or equal to. At x1 and x2. So we're done by a lemma. Our lemma states let f be a function from u times phi to k such that d2 of f is identically 0. Then the character of k being 0 implies f is locally independent of the v coordinate. Proof. Write f locally as a power series as the sum of some f to the alpha sub alpha of y times x to the alpha. Then d2 of f being 0 implies d2 of f alpha is 0 for all alpha. And we show that f alpha is equal to some constant c alpha. First off, note we have reduced our lemma down to f being one of our f alphas. So we can write f as the sum of b sub betas times y to the beta. Then d of f being 0 implies that beta sub I, b sub beta equals 0, where beta is split into coordinates beta I from 1 to r, and I being the range of 1 through r. Since the character of k is 0, then b of beta is 0 for beta non-zero. So f is constant. Now if we note that our phi from our theorem may be written as v1 times u2 onto v1 onto v1 times v2 with the first map being pr sub 1 and the second being the identity of v1 times c. The first map being a submersion and the second being an immersion. And so we're actually now done our theorem. And we have a couple corollaries to follow up on this here. First corollary. Once again, this is exclusive to character 0. Then the x in x with phi being a submersion is dense in x. The proof that x prime be the set of x and x, or phi is submersion, and put f of x to be the rank of tx of phi by the previous theorem. Oh, it's a phi being a subimmersion, not a phi being a submersion. The previous theorem X prime is the set. I wonder if you can hear that. A set of elements of X with F locally constant. We're done by the following two properties of F. First off, we see that F takes integral value and is locally bounded. And secondly, F is lower semi-continuous. And we have another corollary, which is immediate. And here, once again, we're in character 0, and phi being injective. A set of points of X and X with phi being an immersion is dense in X. And with that, that is an episode's length. Next time we're going to look at actually constructing some manifolds now, some various techniques in that. Theorems, pretty exciting. Look forward to that next time. Thanks for watching.